This is actually lesson 8. It's kind of a, normally you wouldn't get this form of an introduction to this until grad school. But that's only because we've only had about 50 years to think about this. I always love to say this. I don't think I've talked about this. You've got the cutting edge of research. You've got the bleeding edge of research. You've got the scabbed edge of research. You have the scarred edge of research. You have the healed edge of research. And then you have education. Right? So a lot of times education is, and this is why a lot of students will ask, like, why is it so hard to understand what I would do out in the world if all I'm doing is taking classes? Computer science and engineering is a little bit better because we spend a non-trivial amount of time to make this connection. Mathematics is notorious bad at this, right? We only had in mathematics 50 years, 50, 60 years to develop this theory. And so right now, most of the context in linear algebra is taught with a lens of the 1950s, which really was based in the 1930s in terms of the math. And so that, I don't blame anybody, but I'd like to be part of the generation of scholars that solves that problem to actually, when you finish my linear algebra class, I want you to be functional. I don't want you to have to go back and relearn all of linear algebra if you actually choose to do this. And so that's what you're kind of seeing here. It's a different approach to linear algebra. So my claim is by identifying special structures in the entries of a matrix, in the entry and format of matrices, we can learn to develop and customize algorithms to solve our fundamental problems based on the features of the matrices involved. And this is a non-trivial thing. Stop, Jeff. Okay, so the first thing we're going to do is we're going to start to introduce some terminology to discuss what rectangular matrices look like. So let's let m and n be an element of the natural numbers. For a rectangular matrix, A element of R m by n, how many rows does it have and how many columns does it have? The row and column dimensions tell us something about the format of a matrix. And we're going to break these into really 3 different patterns, and these 3 different patterns will be used to kind of give us some insight into the type of problem we're working with. A matrix is tall and narrow if m is strictly greater than n. What does that mean? Yeah, tall and narrow matrices have more rows than columns. And I could actually draw this thing A11, A21, sorry about that. What comes first, row index or column index? Row index. So now I got A12, A1. How many total rows does this thing have? Columns, I mean? N. Okay, now we go down to A21, A22, all the way down to A2n. And then for sure I know that there are going to be more rows than columns, and so I can actually say to myself, okay, so this is going to be if this thing was square, but it's not square. How do I know it's not square? Yeah, so in the case that m is equal to n plus 1, I have one more of them, but I can actually have many, many more than just n plus 1. I can have as many as I'd like, right? Can you see why we call this thing a tall and narrow matrix? Yeah, because there's more rows than there are columns, so it's kind of elongated. All right. Could you guess what the next case would be? And why don't we just take the next, what's the next case that you might have? Yeah, why don't we do equal to? If m equals to n, we say a is square, and you got to be careful, not necessarily non-singular. We'll come back to that. All non-singular matrices are square, not all square matrices are non-singular. Since A has the same number of what and what? Same number of rows and columns. In this case, could you guess how we write A? So you would write A11, A12, all the way down to A1n, A21, A22, all the way down to A2n. And then down here we would have AN1. How come I didn't use M there? Yeah. And there's an author called Trefethen that would be mad at me. He likes to say that we should always have the row number be equal to M, but forgive me for choosing N, just a pattern that I'm going to have. All right, so we have what we call tall and narrow. We have square. Could you guess what the third option might be? Let's use a better word than that one. Yeah, try again. Short and wide. Yeah, the US nutrition market just ruins that concept. And so does every single picture that I've ever seen of a model in a... We got to work on our concept of beauty in the United States to include human beings. All right, so a matrix is short and wide if, what would we say? M is less than n. In this case, what would we say about A? A has more what than what? Columns than rows. With, and if we were to actually draw this thing out, what would we say? Okay, first we might start with 1, 1, 2, 1, all the way down to M1, and then we would go to the second column, which would be 1, 2, 2, 2, all the way down to M2, and then eventually I could get to a space where I did what? 1M, 2M, all the way down to MM. Would I stop there in this case? No, because we definitely know that there are going to be more columns. So the square matrix that would be formed, an m by m square matrix, there are definitely going to be columns addended to that or appended to that, right? And what would it all go down to at the end? 1n, 2n, all the way down to... Okay, can I just, I don't want you to care about this today. I'm not going to say this right now, but can I tell you something immediately? One of the first things that I see when I see a tall and narrow matrix, I think to myself, least squares problems. Almost immediately, right? When I see a tall and narrow matrix, usually it's a least squares problem. When I see a square matrix, do you know what I'm thinking in the background? Pretty please with sugar on top. Non-singular system problem. Please, 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 please. Non-singular linear systems, non-singular matrices are the most beautiful matrices that exist from the standpoint of solving backward problems. And so if I see a square matrix, it's in the running, right? If it's not square, what do I know immediately? Not non-singular for sure, right? But if it's square, I'm thinking to myself like, please let it be non-singular. If it's short and wide, you know what I'm thinking almost immediately? General linear systems problem, almost immediately. It's not always the case. These are general rules, not they're not carved in stone. It's not every time it's the case going to be this way. But these are kind of useful things. When I see tall and narrow, least squares. When I see square, praying for non-singular. When I see short and wide, usually general linear systems problems. So that's why I want to set that kind of in the background.